Among the most captivating challenges for astronomers is the task of observing star formation as it happens. Unlike many dramatic cosmic events that unfold over moments or days, the birth of stars takes place over millions of years, a timescale that seems vast by human standards but is relatively brief in the life of the universe. Yet, by using sophisticated technology and clever observational techniques, scientists can piece together a vivid picture of stellar nurseries, regions dense with gas and dust where new stars ignite. Although we cannot watch a single star flicker on in real time, astronomers can observe various stars at different stages of their formation to effectively witness star formation in action across the cosmos. To begin with, the very locations where stars form offer astronomers valuable clues. Stars are born within dark clouds of cold molecular gas and dust called molecular clouds, sometimes called stellar nurseries. These clouds can be enormous, spanning dozens or even hundreds of light years across. Their cores are often so thick with dust that visible light cannot penetrate them, making these regions appear as dark patches against the brighter backdrop of the galaxy when viewed with optical telescopes. Despite this apparent invisibility, these clouds shine brightly in longer wavelengths such as infrared and radio, which can pass through dust layers. Infrared astronomy is particularly vital for studying star formation. Many space telescopes, such as the Spitzer Space Telescope and the more recent James Webb Space Telescope, are designed to observe infrared light. This kind of radiation reveals warmth emitted by young stars glimmering inside their dusty cocoons. For instance, when a protostar begins to form inside a collapsing clump of gas, its increasing internal heat causes the dust around it to glow at infrared wavelengths. Infrared observations thus allow astronomers to peer inside clouds that are otherwise opaque, catching glimpses of newly forming stars hidden from view in visible light. In addition to infrared, radio waves are crucial in examining molecular clouds. Radio telescopes detect the faint signals from molecules such as carbon monoxide, CO, which abound in these clouds. By mapping these molecules' distribution and movements, astronomers can identify areas of dense gas where stars are likely to emerge. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile provide incredibly detailed images of these regions, tracking gas flows and uncovering clumps of star-forming material with remarkable precision. These observations help scientists confirm where collapse is underway, marking the earliest phases of star birth. Besides simply locating star-forming regions, astronomers study the various stages of star formation by identifying characteristic features and emissions that signal specific phases. For example, protostars, objects in the earliest phases of star formation, often reveal themselves through jets and outflows. As gas collapses under gravity to form a protostar, some material is ejected at high speeds along the star's rotational axes. These jets glow in specific spectral lines detectable at optical and radio wavelengths. By observing these outflows, astronomers can identify very young stars still embedded in their gas envelopes, revealing active star formation sites. Another valuable tool in observing star formation involves using spectroscopy, the analysis of light spectrum to determine the physical properties of distant objects. By breaking light from stellar nurseries into its component colors, scientists can detect the fingerprints of different elements and molecules at work, such as hydrogen, helium, carbon, or oxygen, and learn about conditions like temperature, density, and motion. For instance, the hydrogen atoms in ionized gas around new stars emit a well-known red light called the H-alpha emission. Detecting this glow signals the presence of young, hot stars whose intense ultraviolet light energizes the surrounding gas, a sign that the star is reaching a more mature phase. Beyond individual stars, astronomers also observe entire clusters of young stars forming together within molecular clouds. These clusters unveil how stars often don't form in isolation, but rather in groups that may contain hundreds or thousands of stars at similar stages of development. Observing these clusters helps scientists understand the interplay of environmental factors during star formation, how gravity, magnetic fields, turbulence, and radiation influence the birth and early evolution of stars. For example, in regions like the Orion Nebula, a well-studied nearby star-forming region, telescopes have revealed a crowded nursery bustling with protostars, infant stars, and their surrounding disks from which planets may eventually form. While stars themselves take millions of years to form fully, interstellar phenomena associated with their birth can change on much shorter timescales, allowing astronomers to observe developments happening in real time. For instance, the brightness of young stars can vary due to changes in accretion rates, the infall of gas and dust from the surrounding cloud onto the growing star. These shifts in brightness, called variability, can occur over days, weeks, or months, providing astronomers with interesting signals about the dynamic environment of star formation. Monitoring these changes with long-term observational campaigns enables researchers to learn how stars gather material and evolve during their earliest chapters. Similarly, the expansion of bubbles or cavities within molecular clouds, carved out by radiation and stellar winds from massive young stars, is another evolving feature that astronomers can track. Over years or decades, these changes can be mapped with images taken at different times, revealing how energetic young stars start to clear out their surroundings, influencing future generations of star formation nearby. This feedback process plays a critical role in shaping the life cycle of star-forming regions. Space-based telescopes, including the Hubble Space Telescope, have made invaluable contributions by capturing detailed images of star-forming regions at various wavelengths. Hubble's high resolution has produced iconic images of star birth, such as the Eagle Nebula's Pillars of Creation, where dense columns of gas are incubators housing infant stars. Viewing these pillars at multiple points in time lets astronomers detect subtle changes that hint at internal processes reshaping the structure, further evidence that star formation is an ongoing, active phenomenon. Ground-based observatories, in combination with space observatories, also help astronomers study star formation. Adaptive optics technology corrects for the twinkling effect caused by Earth's atmosphere, enabling telescopes like those on Mauna Kea in Hawaii to observe protostars and their disks with remarkable clarity. Observations of protoplanetary disks, the swirling rings of material around infant stars, offer insights into how planets may form alongside stars, putting star formation in a richer context that links stellar birth to the eventual creation of planetary systems like our own. By combining data from multiple telescopes working across the electromagnetic spectrum, radio, infrared, visible, ultraviolet, and even X-rays, scientists assemble a comprehensive view of how stars come to be. Each wavelength unveils a different aspect of the process, much like viewing a complex phenomena through specialized glasses that reveal hidden layers. This multi-wavelength approach is essential for understanding the many physical processes shaping star formation, from the collapse of gas clouds to the ignition of nuclear fusion at a star's core. In recent years, advances in technology and techniques such as computer modeling have complemented observations by providing a theoretical framework to interpret what astronomers see. Simulations of star formation take into account gravity, turbulence, magnetic fields, and chemistry, making predictions that observers can compare against real data. This feedback loop between observation and theory sharpens scientists' ability to decode the clues from distant stellar nurseries and better understand the mechanics driving star birth. Ultimately, the combined observations and studies reveal that star formation is a complex, multi-stage process involving the interplay of physical forces and chemical reactions spanning massive scales of time and space. Although we cannot watch a single star ignite within a human lifetime, by observing numerous stars at different points along their path and examining the evolving environment of molecular clouds, astronomers effectively witness star formation as an active and ongoing cosmic event. With powerful new observatories coming online and innovative techniques continually improving, our ability to observe star formation is entering an exciting era. Every new image or spectrum brings us closer to understanding how the universe transforms clouds of gas and dust into the brilliant stars lighting up the night sky. A process that underpins not only the cosmos at large, but also the origins of the solar system and life itself. A crucial element in the story of star formation is the gravity-driven collapse of molecular clouds, the earliest and most essential step in bringing a star into existence. Within the immense cold clouds of gas and dust, certain regions can become unstable and begin to contract under their own gravity. This process transforms diffuse clouds into dense knots, setting the stage for star birth. But this collapse is far from a simple, uniform shrinking. It's a dynamic, turbulent event influenced by a variety of physical factors. Gravity works against internal forces attempting to keep the cloud from collapsing. For a molecular cloud to begin contracting significantly, it must overcome the opposing pressure exerted by the gas particles themselves, as well as magnetic fields threading through the cloud and turbulence caused by chaotic gas motions. In this context, turbulence does not stabilize the cloud, but instead creates a patchwork of varying densities and pressures, forming localized pockets where gravity gains the upper hand. Within these knots, material draws inward, gradually increasing the density and temperature at the center to spark the birth of a protostar. Scientists often use a concept called the gene's instability to predict when and where a cloud or subregion within it will collapse to form stars. Named after British physicist Sir James Jeans, this criterion compares the internal pressure within a cloud to the gravitational force acting to compress it. When the cloud's mass or size exceeds a certain threshold, now called the Jeans mass or Jeans length, respectively, gravity dominates, triggering collapse. This calculation explains why not every patch of a molecular cloud forms a star, and why clouds fragment into clusters of stars, rather than collapsing as a whole. Alongside gravitational physics, magnetic fields play a critical role in this early stage. These fields, while invisible to the eye, thread through interstellar space and can slow the collapse of clouds by exerting magnetic pressure and tension. Magnetic fields can channel material along field lines, influence how gas flows into dense cores, and even affect the final rotation of forming stars. Observations with instruments like ALMA have allowed astronomers to map magnetic field structures in molecular clouds by detecting polarized light emitted by dust grains aligned with magnetic fields, offering valuable insights into their complex role. As the collapse proceeds, the central region of the dense core forms what is known as a protostar, a hot, dense object that has yet to ignite nuclear fusion in its core. At this stage, the protostar is still growing by sucking in gas and dust from the surrounding envelope, a process called accretion. Material spiraling inward forms a rotating disk around the protostar as a natural consequence of conservation of angular momentum, much like an ice skater pulling in their arms to spin faster. These circumstellar or protoplanetary disks not only feed the growing star, but also serve as the birthplaces of future planets, tying the story of star formation directly to planetary systems. Accretion disks are of keen interest because they hold clues about how our own solar system originated. Observations of young stars surrounded by these disks allow astronomers to study how dust grains collide and stick together, potentially forming the building blocks of planets, pebbles, boulders, and eventually fully formed planetary bodies. Different wavelengths reveal different aspects of these disks. Infrared light traces the warm dust, millimeter and submillimeter wavelengths detect the cooler, larger particles, and radio observations can identify molecules such as carbon monoxide or water vapor, indicating chemical processes within the disk. One fascinating feature of many protostars is the presence of bipolar jets, narrow streams of gas launched at high speeds perpendicular to the rotation plane of the accretion disk. These jets stretch light years into interstellar space, carving out cavities within the molecular cloud and interacting with the surrounding gas. The exact mechanism behind jet formation is complex, involving magnetic fields anchored in the disk or star tapping into rotational energy. These jets act as a release valve, carrying away angular momentum and allowing matter to continue falling onto the star, effectively regulating star growth. Jets also produce shock fronts where they collide with surrounding gas, leading to bright emission regions called Herbig-Haro objects. These glowing spots were first identified in the mid-20th century and remain key signposts of active star formation. By studying these jets and their interactions, astronomers can estimate the speed and quantity of material ejected, gaining insight into how protostars influence their environments. Importantly, feedback from jets and stellar winds begins to reshape the natal cloud, dispersing gas in some areas while compressing it in others, potentially triggering new rounds of star formation. As the protostar grows and its core temperature climbs, it eventually reaches around 10 million degrees Celsius, the threshold for igniting hydrogen fusion. This fusion reaction, where hydrogen nuclei combine to form helium while releasing enormous energy, marks the transition from a protostar to a true star entering the main sequence phase of its life. At this point, the outward pressure from fusion-generated radiation balances the inward pull of gravity, achieving hydrostatic equilibrium that stabilizes the star. But reaching this milestone does not necessarily happen quietly or smoothly. In some cases, young stars undergo periods of unstable accretion, where large amounts of matter suddenly fall onto the star, dramatically increasing its brightness, a phenomenon known as an FU Orionis outburst after the prototype star FU Orionis. These outbursts can last for decades, and astronomers believe they play a significant role in how stars accumulate mass. Changes in brightness are not limited to outbursts. Many young stars exhibit variability on shorter timescales due to rotating star spots, changes in accretion rates, or obscuration by dust in their orbiting disks. By comparing stars at various points along these early stages, scientists construct a classification scheme, a sequence known as the protostellar classes, that reflects the evolution of young stars from deeply embedded objects to visible stars surrounded by thinning disks. In this system, Class 0 objects represent the earliest, deeply shrouded objects still gaining mass, followed by Class I, where the protostar is gaining prominence, Class II characterized by a clear star with a substantial disk, and Class III where the disk has mostly dissipated. This classification acts as a roadmap, allowing astronomers to place observations into clear evolutionary context. Surrounding these individual stars, the ecological impact of star formation unfolds on larger scales. Massive young stars, those many times more massive than our Sun, have immense effects on their stellar neighborhoods. Their powerful ultraviolet radiation ionizes nearby gas, creating glowing regions called HII regions. The radiation pressure coupled with strong stellar winds can shape the structure of molecular clouds, creating bubbles or pillars, as seen in iconic nebulae. These processes can trigger the collapse of adjacent cloud material, seeding the birth of new stars, or conversely can blow away gas, quenching star formation locally. The influence of massive stars extends beyond individual molecular clouds, shaping entire star-forming regions and the evolution of galaxies over time. Supernova explosions, the violent deaths of these most massive stars, return heavy elements forged in their cores back into space, enriching the interstellar medium with the ingredients necessary for new stars, planets, and ultimately life. In this way, the cycle of star formation and stellar death drives the chemical evolution of the universe, continuously renewing and transforming galactic ecosystems. At the heart of this process lies a remarkable balance of forces and energies. Gravity pulls inward, attempting to build stars. Thermal pressure pushes outward, resisting collapse. Magnetic fields and turbulence add complexity. Radiation and winds act as feedback mechanisms, and chemical reactions both cool and heat the gas. This interplay leads not only to the formation of stars, but also determines their masses, multiplicity, single stars or multiples, and the character of their planetary systems. While modern technology provides exceptional ways to observe these processes, much remains to be uncovered. Star formation is a fundamentally three-dimensional and highly dynamic process, making it challenging to capture in its entirety. Advances in technology, including more sensitive detectors, higher resolution imaging, and computational power, enable astronomers to simulate and visualize star-forming regions with ever-increasing fidelity. These models help interpret observations and test theories about the physical mechanisms at work. In addition to the stars themselves, the chemical environment of molecular clouds is a rich area of study. Molecules ranging from simple hydrogen and carbon monoxide to complex organic compounds exist within these clouds and their protoplanetary disks. Astrochemistry bridges astrophysics and chemistry, examining how molecules form, survive, and transform in space. This field sheds light on why some regions are more conducive to star and planet formation, and explores the origins of the prebiotic molecules essential to life. Measurements of molecular abundances can also trace different temperatures and densities inside clouds. For example, nitrogen-bearing molecules are often found in the coldest, densest regions, while others signal environments heated by nearby young stars. Recent discoveries of complex organic molecules in protoplanetary disks even hint at the chemistry that ultimately seeds emerging planetary systems with the ingredients needed for life. Taken as a whole, observing star formation requires a multidisciplinary approach blending physics, chemistry, computational modeling, and technological innovation. Space-based and ground-based observatories complement each other, and upcoming projects promise to accelerate progress. For instance, future large telescopes like the Extremely Large Telescope, ELT, and space missions focusing on the far-infrared and submillimeter wavelengths will open new windows onto the cold regions where star formation is hidden from view. As our understanding deepens, star formation remains one of the most profound examples of nature's ability to organize complexity, from diffuse clouds of simple atoms into radiant stars with planetary systems. These transformations underpin the very existence of galaxies, planetary systems, and life's building blocks, connecting the fundamental physics of gas and dust with the cosmic story of creation. Through the steady efforts of observational astronomers and theorists alike, we continue to witness star formation not just as an abstract process, but as an active, intricate phenomenon shaping the universe around us. A particularly intriguing aspect of star formation comes from examining the role of turbulence within molecular clouds. While gravity steadily pulls gas and dust inward, turbulence injects a chaotic energy that can both delay and facilitate collapse. Rather than being a simple antagonist to star birth, turbulence generates a complex web of dense filaments and knots within clouds. These filaments can funnel material into concentrated regions, helping to initiate the formation of dense cores that eventually become protostars. High-resolution observations, especially from ALMA, have revealed the intricate filamentary networks threading through star-forming clouds, emphasizing that stars rarely form in isolation, but within these elongated structures born of turbulent flows. Turbulence arises from several sources: supernova explosions, stellar winds from young massive stars, galactic rotation, and even previous episodes of star formation. When massive stars near the end of their lives explode as supernovae, the resulting shock waves propagate through the interstellar medium, stirring the gas and injecting kinetic energy. This energetic feedback can compress portions of molecular clouds, triggering pockets of gravitational collapse, but it also disperses material in other regions, halting star birth. Thus, turbulence and stellar feedback act together to regulate the rhythm of star formation throughout the galaxy. The filamentary structures created by turbulence are not merely fleeting features, but appear vital to the star formation process. Observations of nearby star-forming regions show that these filaments often have unusually uniform widths of about 0.1 light-years, regardless of their length or density. This surprising consistency suggests some universal mechanism shapes them, possibly linked to magnetic fields and the balance of pressure forces in the gas. Within these filaments, gravity can cause further fragmentation into dense cores with enough material to collapse and start forming stars. Understanding how filaments fragment connects directly to one of the long-standing questions about star formation. What determines the masses of newly formed stars? Observations indicate that the distribution of star masses, the initial mass function IMF, is remarkably similar in different regions of the Milky Way and even in other galaxies. The IMF describes how many low-mass stars form compared to more massive ones, and has implications for galaxy evolution, chemical enrichment, and the type of energetic feedback stars produce. Detailed studies suggest that the fragmentation of filaments into cores largely sets the masses of stars to come. The balance between gravity, thermal pressure, turbulence, and magnetic fields within these filaments influences how large these cores become before collapsing. Small variations in this balance can shift the resulting star mass distribution, meaning star formation is exceptionally sensitive to local environmental conditions despite some overall universality. Moving from dense filaments and cores to the birth of individual stars, we encounter the fascinating phenomenon of accretion variability. Rather than steadily gathering material from their surroundings, protostars often experience dramatic bursts in mass accretion. In these episodic events, the inflow of gas onto the growing star spikes, temporarily increasing its brightness by orders of magnitude. A prime example is Fu Orionis-type stars, young objects that have shown spectacular, sudden increases in luminosity. These brightness jumps can last decades, followed by gradual declines before potentially recurring. These accretion bursts are believed to play crucial roles in stellar growth. They may help resolve the apparent discrepancy between the timescale of star formation and how fast matter can fall onto the star under ordinary conditions. The bursts could be caused by instabilities in the accretion disk, such as gravitational instabilities that redistribute mass suddenly inward. Another possibility involves magnetic effects temporarily impeding and then releasing accretion flows. Monitoring these variable young stars provides valuable insight into star formation dynamics. Long-term observations have been key in identifying and characterizing these changes, with surveys across infrared and optical wavelengths tracking brightness shifts. Variability is not limited to huge outbursts. Smaller fluctuations on days, weeks, or months reflect modulations in accretion rates, star spots rotating in and out of view, or variable obscuration by dust in protostellar envelopes and disks. In tandem with variability studies, astronomers have gained important information about the geometry and composition of the disks surrounding young stars. Protoplanetary disks are composed of gas and dust orbiting the nascent star, and their physical characteristics evolve as material accretes onto the star or forms planets. Observations utilizing millimeter and submillimeter wavelengths have mapped the distribution of dust grain sizes and gas molecules within these disks, revealing processes of dust growth and sedimentation key to planet formation. For example, high-resolution ALMA images of famous disks like the one around HL Tau have shown concentric rings and gaps, suggesting that planets may already be forming and clearing paths in the disk. Other disks display spiral arms or asymmetries hinting at turbulent or gravitational effects. The chemical complexity within disks is profound, including organic molecules like formaldehyde and methanol that are possible precursors for prebiotic chemistry. These molecules, exposed to radiation from the host star, undergo chemical reactions that may provide the ingredients for life's building blocks. Beyond individual protostars and their disks, researchers study star formation on the scale of entire molecular clouds and clusters to understand broader patterns. Star clusters provide opportunities to observe statistically significant samples of young stars at similar distances, but in varied evolutionary stages. This helps astronomers validate models of star formation and early stellar evolution. A striking example is the Orion Nebula Cluster, a nearby giant nursery with thousands of young stars. It displays a range of objects from deeply embedded protostars to newly ignited stars shedding their natal envelopes. In the Orion region, powerful massive stars have carved out cavities and sculpted the surrounding gas, influencing star formation in neighboring clumps. The dynamics within such clusters, close encounters, binary star formations, and interactions with gas affect how stars and their planetary systems evolve. Stellar encounters can truncate protoplanetary disks or alter their compositions, impacting planet formation outcomes. Another critical piece of the star formation puzzle involves feedback mechanisms from young stars, especially the most massive ones. Massive stars, those over 8 times the mass of our Sun, exhibit immense luminosities and energetic outputs. Their ultraviolet radiation ionizes vast volumes of gas, creating HII regions, bubbles of ionized gas that glow vividly in optical and radio wavelengths. The radiation pressure and stellar winds they emit exert mechanical force on the surrounding material, sometimes triggering subsequent star formation by compressing gas in adjacent regions, a process called triggered star formation. However, feedback is a double-edged sword. While it can induce collapse in some areas, it can also erode and disperse molecular clouds, halting star formation by removing the raw material. This delicate interplay shapes the life cycle and efficiency of star formation in galaxies. Moreover, massive stars evolve rapidly, culminating in supernova explosions that inject heavy elements and kinetic energy back into space, influencing the interstellar medium and sowing seeds for new generation stars. The life cycles of molecular clouds themselves are also a subject of intense study. Though clouds may span many light years and contain thousands of solar masses of gas, their lifespans are surprisingly short on cosmic scales, typically a few million years. During this period, the combined effects of gravity, turbulence, magnetic fields, and stellar feedback determine whether a cloud will collapse to form stars or dissipate back into the diffuse interstellar medium. Recent studies using sensitive tracers of molecular gas and dust, along with measurements of magnetic field strengths and structures, are beginning to clarify how clouds evolve and eventually disperse. For example, the observation of expanding shells and superbubbles created by clustered supernovae informs us about cloud disruption timescales and how galactic environments regulate star formation. Stepping back to the galactic scale, star formation rates vary widely across different types of galaxies and epochs in the universe's history. In the present-day Milky Way, stars form at a relatively modest pace of a few solar masses per year. But in starburst galaxies, this rate can be hundreds or thousands of times greater, fueled by abundant molecular gas, often concentrated by galactic interactions or mergers. Large surveys combining multi-wavelength data from instruments on Earth and space reveal correlations between gas content, star formation activity, and galactic morphology. For example, dense molecular gas traced by emission from molecules such as HCN correlates strongly with star formation rates, underscoring the importance of dense gas as the immediate fuel for star birth. The evolution of star formation across cosmic time also shows fascinating trends. Observations of distant galaxies indicate that the universe's star formation rate peaked around 10 billion years ago and has since declined, exploring how molecular clouds form and collapse under different conditions. From the early universe's metal-poor gas to the enriched environments today, remains an ongoing area of research. All these layers of complexity, from turbulent gas filaments to massive star feedback, from individual protostellar disks to galaxy-wide star formation rates, highlight that star formation is a process governed by countless interconnected factors. By unraveling these, astronomers aim to understand not only how stars form, but how the cosmos develops its structure and diversity. Emerging technologies promise to accelerate discoveries in this field. The upcoming James Webb Space Telescope, equipped with unprecedented infrared capabilities, is beginning to peer deeper into star-forming regions with refined sensitivity and resolution. The Extremely Large Telescope, ELT, with its enormous mirror and advanced adaptive optics, will probe the detailed properties of protostars and their environments in unparalleled detail. Additionally, planned missions targeting the far infrared and submillimeter regimes will unveil the coldest and most obscured star-forming environments. In tandem, advances in computational astrophysics allow researchers to simulate star formation processes with increasingly realistic physics. These simulations incorporate magnetohydrodynamics, radiation transport, chemistry, and gravity, creating virtual star-forming clouds that can be directly compared with observations. Such comparisons test theories about the microphysics of collapse, disk evolution, jet formation, and feedback effects. As the synergy between observation and modeling strengthens, our picture of star formation grows ever more nuanced. We are learning to read the cosmos with greater precision, recognizing the signatures of physical laws shaping matter as it condenses into luminous stars. This knowledge not only answers fundamental scientific questions, but enriches our understanding of the journey from simple atoms to the complex structures that ultimately foster life itself. Closely intertwined with the formation of stars is the fate and evolution of the protoplanetary disks that surround them. These disks are the cradles of planetary systems, made up of gas and dust left over from the star's own birth. Understanding the evolution of these disks is crucial for tracing the path from star formation to planet formation, and ultimately to the environments where life as we know it might arise. Protoplanetary disks initially contain a mixture of microscopic dust grains, gases like hydrogen and helium, and a host of molecules including water, carbon monoxide, and a variety of organic compounds. Over time, these grains collide and stick together through a process called coagulation, gradually growing from tiny particles to millimeter-sized pebbles, then to larger rocks and planetesimals, kilometer-sized building blocks of planets. This growth is complex and counteracted by processes such as collisions that can fragment particles or gas drag that causes inward drift of solids toward the star. High-resolution observations with ALMA and other powerful telescopes have revealed remarkable features within these disks that point to ongoing planet formation. Concentric rings and gaps are often visible, sometimes accompanied by spiral arms or clumps. These structures suggest that forming planets are gravitationally interacting with the disk, clearing out lanes and creating resonant patterns. For example, the HL Tau disk, the first to reveal such intricate structure, provided direct observational evidence that planets can carve gaps in disks even around stars less than 1 million years old. In addition to their spatial structure, the chemical composition of these disks is an active area of research. Molecules found in protoplanetary disks range from simple species like water vapor and carbon monoxide to more complex organics such as formic acid and methanol. Studying this chemistry offers clues about the conditions under which planets form, particularly the availability of volatile compounds that might be essential for habitability. Regions within disks can be cold enough for ices to freeze onto dust grains, affecting growth rates and compositions, while warmer inner regions experience photochemistry driven by the young star's radiation. The timescales for protoplanetary disk evolution provide an important constraint on how quickly planets must form. Observations across star-forming regions at different ages indicate that disks typically dissipate within a few million years. This clearing happens as material is either accreted onto the star, blown away by stellar winds and radiation, or locked up in forming planets. The final dispersal is often marked by the appearance of transition disks with large inner holes devoid of dust but retaining material farther out, likely signaling advanced stages of planet formation or disk clearing by stellar activity. Massive young stars with strong radiation fields can accelerate disk dispersal by photoevaporation, where high-energy photons strip gas away from the disk's surface. This effect, combined with accretion and winds, sets a delicate balance determining how long a disk endures and influences the types of planets that might form. For instance, rapid dispersal could limit the time available for giant planet formation, which necessitates substantial gas accumulation before the gas clears out. Another fascinating aspect is that protoplanetary disks do not all look or behave the same. Disk mass, size, temperature profiles, and chemical content vary widely depending on the host star's mass, age, and environment. Surveys reveal differences between disks around low-mass stars, sun-like stars, and massive stars. Each category may follow somewhat different evolutionary paths. External environment matters too. Disks in dense stellar clusters may experience intense ultraviolet radiation from nearby massive stars, leading to faster dispersal compared to isolated stars. In dense stellar environments such as the Orion Nebula cluster, astronomers observe a phenomenon called proplids, short for Proto-P-Lanatar Y disks. These are young stars with disks that appear as bright, glowing teardrop-shaped objects, shaped by the harsh radiation of nearby massive stars. The external radiation ionizes the disk surface, driving strong photoevaporative flows that strip material away. These observations underscore how star formation environment can influence the early evolution of planetary systems, potentially affecting the kinds of planets formed. The emergence of planets from disks is intimately linked to angular momentum transport, which governs how material moves inward toward the star or outward to form planets. While accretion onto the protostar requires gas in the disk to lose angular momentum, how efficiently this occurs is an area of active research. Various physical mechanisms are proposed, including turbulence driven by magnetic fields, magnetorotational instability, gravitational instabilities in massive disks, and disk winds potentially powered by magnetic fields or stellar irradiation. Understanding these processes is essential because they affect disk lifetimes and the pace of planet formation. In addition to observations, computer simulations have played a key role in exploring protoplanetary disk evolution and planet formation. Models track dust grain growth, disk chemistry, gas dynamics, and planet-disk interactions under different conditions. Simulations predict how planets carve gaps, migrate within disks, and accumulate atmospheres. Comparing these models to observations refines our understanding of diverse planetary systems observed in the galaxy, including why some stars host giant gas planets, while others only have smaller, rocky worlds. Indeed, the direct imaging of exoplanets has now revealed a range of planetary systems, validating the idea that star formation is closely tied to planet formation. Some young systems display massive planets still embedded within or near their natal disks, offering a window into early planet-disk interactions. These findings fuel the broader quest to understand the origins of planetary architecture and the conditions that make Earth-like planets likely or rare. Beyond planets, the dust and gas dynamics within protoplanetary disks influence the formation of smaller bodies such as comets and asteroids. These remnants can serve as reservoirs of primordial material, preserving clues about the early solar nebula's chemistry. Studying dust grain properties, compositions, and movements helps astronomers piece together the early ingredients available for planet building and the delivery of volatiles like water to terrestrial planets. In connecting star formation and planet formation, the role of magnetic fields remains crucial. Magnetic fields not only shape the accretion flows onto the star and disk, but may also influence the growth and migration of solids within disks. Polarimetric observations sensitive to dust grain alignment help map magnetic field lines within disks, revealing complex spatial structures that connect to the larger-scale fields threading molecular clouds. These magnetic influences may affect planetesimal formation efficiency and the stability of disks. The study of disks and planet formation also extends to examining the end states of disks. the debris disks that remain after the primary gas-rich protoplanetary phase fades away. Debris disks are composed mainly of dust generated by collisions among leftover planetesimals, such as asteroids and comets. Observations of debris disks give insight into the evolution of planetary systems over tens to hundreds of millions of years, highlighting how planetary dynamics continue to shape these systems long after star formation concludes. Investigations of star formation and disk evolution find exciting new dimensions when considering multiple star systems. Stars rarely form alone. Binary and multiple star systems are common outcomes of cloud collapse and fragmentation. How disks evolve around stars in binary or multiple systems presents challenges for planet formation. Disks can be truncated, warped, or disrupted by gravitational interactions, potentially influencing planet mass and orbital dynamics. Observations have found circumbinary disks orbiting beyond two or more stars, as well as circumstellar disks surrounding individual components, each with distinct characteristics. A further frontier explores the earliest observable stages of disk formation right after protostars emerge. Initially, infalling gas carries angular momentum into the region, spinning up and forming a disk inside the collapsing envelope. However, the earliest disks are often small and heavily embedded in dust, making them difficult to observe. Observatories like ALMA now detect these nascent disks, contributing to a better understanding of how disks form rapidly after collapse begins, and how their properties evolve during the protostellar accretion phase. While the focus here has been on protoplanetary disks around sun-like stars, disks and planet formation are also studied around stars of different masses. Around very low-mass stars and brown dwarfs, disks are smaller and less massive, potentially limiting planet formation. Conversely, massive stars form with strong radiation and energetic environments that can strip or heat disks quickly, posing challenges for planet survival. The diversity of disk properties across stellar types broadens our perspective on planetary system formation in the galaxy. By integrating these findings, astronomers build a more complete narrative linking star formation to the emergence of complex planetary environments. The early life of a young star, shrouded in collapsing gas and dust, naturally gives rise to disks varying widely in size, mass, chemistries, and dynamics. These disks, through millions of years of evolution, set the stage for the formation of planets, asteroid belts, and possibly habitable worlds. This ongoing research underscores star formation's essential role as the first step not just in stellar life, but in the cosmic progression toward the diverse planetary systems observed today. As observational capabilities continue to advance, especially with facilities capable of resolving ever finer details in disks and their chemistry, our understanding of the intertwined stories of stars and planets deepens, bringing us closer to answering fundamental questions about our own origins in the cosmos. While much attention focuses on the formation and evolution of individual stars and their surrounding disks, another crucial dimension of star formation lies in understanding how entire clusters and stellar populations emerge from molecular clouds. Most stars in the universe, including our own sun, form not in isolation, but as part of clusters containing hundreds or thousands of stars, all born within roughly the same time frame and from the same reservoir of gas. Studying star clusters offers insight into the collective processes that govern how star formation operates on a larger scale, and how the earliest environments influence the future evolution of stars and their planetary systems. Star clusters come in a variety of sizes and densities. Open clusters, such as the Pleiades, are relatively loose groupings of young stars, often visible as bright, scattered points in the night sky. These clusters typically contain from a few dozen to a few thousand stars, and may remain bound gravitationally for hundreds of millions of years before dispersing into the galactic field. In contrast, much denser clusters called globular clusters consist of hundreds of thousands to millions of stars, but these are mostly ancient populations formed very early in the history of the galaxy, not the sites of current star formation. For understanding current star formation, the focus is on young star clusters nestled within molecular clouds. These clusters reveal many features that cannot be studied by looking at a single star alone. For example, cluster environments often include massive stars, whose intense radiation and powerful stellar winds dramatically reshape their surroundings. When massive stars emerge within a cluster, their energetic feedback can drive ionization fronts and shockwaves through the remaining gas, potentially triggering new waves of star formation in neighboring dense clumps, or, conversely, dispersing gas and halting star formation locally. This feedback dynamic creates an intricate temporal and spatial interplay between different generations of stars. Studies of nearby regions such as the Orion Nebula cluster show that massive stars influence protoplanetary disks around lower-mass stars, sometimes prematurely stripping away the disk's gas and thereby possibly limiting planet formation. This external photoevaporation can affect how many planetary systems in the cluster can develop fully, underscoring that star formation environments are not neutral backdrops, but active participants shaping outcomes. Cluster dynamics also influence stellar encounters during the early stages. In dense clusters, forming stars and their newborn planetary systems are packed relatively close together, increasing the likelihood of gravitational interactions. Such encounters can perturb or truncate protoplanetary disks, strip outer planets from their orbits, or even form binary and multiple star systems through captures or exchanges. These interactions help explain the wide variety of binary star configurations and may contribute to the diversity seen in exoplanet systems. On larger scales, the initial conditions within a molecular cloud, including its total mass, turbulence, and magnetic field structure, set the stage for the mass distribution of stars within a cluster. This distribution, known as the initial mass function, IMF, describes the relative numbers of stars formed at different masses. Observations indicate that the IMF is surprisingly consistent across a range of star-forming environments, suggesting some universal physical regulation. Yet, subtle variations in the IMF or cluster properties may emerge depending on local conditions, adding complexity to our understanding of how universal or varied star formation truly is. Monitoring young clusters also provides the opportunity to examine how stars evolve together. Since cluster members share the same approximate age, comparing their properties helps astronomers understand early stellar evolution phases and the timescales of disk dispersal, accretion halts, and magnetic activity changes. For example, variations in stellar rotation rates seen in clusters provide clues about angular momentum loss via stellar winds and disk interactions. Furthermore, star clusters can inform us about the formation of massive stars themselves, a topic still full of open questions. Massive stars form deeply embedded inside dense cores, often near the centers of clusters, where conditions for rapid accretion prevail. Because forming massive stars often continue accumulating mass while already emitting intense radiation and driving powerful outflows, understanding how they overcome radiation pressure and form efficiently remains an active research frontier. Observations of massive young stellar objects and their environments contribute to refining theoretical models of this complex formation process. Zooming out even further, star formation in clusters ties directly to the large-scale structure of galaxies. Molecular clouds often organize along spiral arms or dense galactic features, forming chains or complexes of clusters that collectively influence galactic evolution. In starburst galaxies, galaxies with extraordinarily high rates of star formation, massive clusters known as superstar clusters can contain tens of thousands or even millions of young stars. These clusters are extreme environments where feedback effects are magnified, shaping the host galaxy's interstellar medium on kiloparsec scales. To understand these broader themes, astronomers utilize extensive surveys combining optical, infrared, and radio observations to identify star clusters across our galaxy and beyond. These surveys help chart how star formation efficiency, How much of the available gas converts into stars varies with environment, gas density, and galaxy type. They also provide vital statistics about stellar multiplicity, cluster lifetimes, and dispersal mechanisms into the galactic field. In recent years, the study of star clusters has increasingly benefited from data provided by the European Space Agency's Gaia mission. Gaia's precise measurements of stellar positions, distances, and motions allow astronomers to unravel the three-dimensional structure and dynamics of young clusters with unprecedented accuracy. This capability reveals how clusters form, expand, or contract over time, and how stars escape their birthplaces to populate the wider galaxy. It also enhances our ability to identify coeval groups of stars even as they disperse, helping reconstruct star formation histories. As we deepen our understanding of star clusters and their environments, another intriguing layer has been added by the discovery of chemically distinct subpopulations within some clusters. In some massive clusters, stars show variations in elemental abundances that suggest multiple star formation episodes or complex gas mixing histories. While these features are most prominent in ancient globular clusters, searching for analogous phenomena in younger clusters offers a window into feedback and gas recycling within stellar nurseries. Altogether, examining star formation within clusters integrates many strands of research: individual star and disk evolution, dynamics, feedback mechanisms, and galactic context, creating a richer, more holistic picture of how stars are born. Clusters serve as natural laboratories where physical processes interplay on many scales, from the microphysics of collapse to galactic-scale feedback loops. As observational capabilities continue to advance, new instruments and surveys will provide even finer detail and broader statistical samples of cluster properties. Upcoming facilities, like the Vera C. Rubin Observatory with its unparalleled time-domain survey capabilities, will catch fleeting variability and eruptive events in young clusters, shedding light on the episodic nature of accretion and early stellar activity. Meanwhile, next-generation infrared and radio telescopes will probe the densest cluster cores, where the earliest stages of star and massive star formation are deeply hidden at shorter wavelengths. Through combined observational and theoretical efforts, astronomers are piecing together how molecular clouds fragment into star clusters, how different stellar masses arise within them, and how the feedback from newborn stars sculpts their birth environments. This knowledge helps trace the cosmic cycle by which gas converts into stars, which then enrich and regulate subsequent generations of star formation, ultimately shaping the appearance and evolution of galaxies. Understanding star formation in clusters also has important implications beyond astrophysics. Since the majority of stars, and by extension their planets, form in such environments, this research informs our grasp of planetary system architectures, potential habitability, and the frequency of life-bearing worlds in the universe. Conditions within clusters, such as proximity to massive stars or intense radiation fields, may influence not only planet formation, but also planetary atmospheres and early climate conditions. In sum, the birth of stars within clusters represents a vibrant, multifaceted aspect of cosmic star formation. These stellar families bear witness to the interplay of fundamental forces, complex feedback systems, and dynamic environments that shape the universe's luminous constituents. By studying clusters, we bridge microscopic processes of gas collapse and chemistry with the grand scales of galactic evolution, enhancing our understanding of how stars, like our Sun, come into being as parts of intricate cosmic communities. In addition to the formation and evolution of individual stars and their clusters, exploring the connection between star formation and the larger galactic ecosystem provides a crucial perspective on how the universe organizes matter on grand scales. Star formation does not happen randomly throughout a galaxy. Instead, it is closely linked to the distribution and dynamics of the interstellar medium, the vast expanse of gas, dust, and cosmic rays filling the spaces between stars. Understanding how star formation operates within this environment reveals much about galaxy evolution and how the cosmic cycle fuels the growth of structure over billions of years. Galaxies themselves have varying patterns and rates of star formation that depend on their type, age, and environment. Spiral galaxies, like the Milky Way, feature prominent arms where dense molecular clouds and dust accumulate. These spiral arms act as sites of enhanced star formation, compressing gas through the passage of density waves. As clouds enter a spiral arm, they experience increased pressure from the accumulated material, which can trigger the gravitational collapse of molecular clouds, leading to new stars igniting. This process helps explain why spiral arms appear so bright and filled with young, hot stars compared to the more diffuse interarm regions. In contrast, elliptical galaxies generally exhibit very low rates of star formation. These galaxies are often dominated by older stellar populations and contain less cold molecular gas, the essential raw material for star birth. Their star-forming phase likely ended billions of years ago after using up or losing most of their gas through galactic interactions or energetic events. Understanding this transition from active star formation to quiescence remains an active area of research, highlighting how galaxy-scale phenomena regulate the availability of star-forming fuel. Even within spiral galaxies, star formation rates vary substantially across regions, depending on local gas density, dynamics, and feedback from existing stars. Observations show that not all molecular clouds form stars equally efficiently, a metric known as the star formation efficiency, SFE. Some clouds collapse vigorously, producing clusters of stars relatively quickly, while others remain quiescent for extended periods. This variation reflects how complex factors such as turbulence, magnetic fields, and stellar feedback orchestrate the interplay between gas inflow, collapse, and dispersal. Feedback from stars plays an outsized role in regulating star formation on galactic scales. Massive stars, in particular, inject energy back into the interstellar medium through their intense ultraviolet radiation, stellar winds, and eventual supernova explosions. This injection of energy stirs the gas, sustaining turbulence within the galaxy and preventing all molecular clouds from collapsing simultaneously. Such regulation maintains a balance that prevents the rapid exhaustion of gas and allows galaxies to sustain star formation over long periods. Additionally, supernovae enrich the interstellar medium with heavy elements, what astronomers call metals, that are key to the next generation of star and planet formation. Elements like carbon, oxygen, iron, and others are forged in the cores of massive stars and dispersed into space when these stars explode. This chemical enrichment influences the cooling properties of clouds, their ability to form molecules, and ultimately the composition of planets that emerge around new stars. Without this cycle, the universe would be far less hospitable to the complex chemistry associated with life. On larger cosmic scales, interactions between galaxies can dramatically influence star formation. When galaxies collide or pass near one another, gravitational forces compress clouds and funnel gas into their central regions, often triggering intense bursts of star formation known as starbursts. These events can create massive clusters of stars in a relatively brief cosmic moment, profoundly impacting the morphology and evolution of the galaxies involved. The Antennae galaxies are a classic example, where tidal interactions between two merging galaxies produce spectacular regions of concentrated star formation seen in vivid detail. Meanwhile, observations of galaxies in the distant universe, looking back billions of years in time, show that star formation peaked around 10 billion years ago during what astronomers call cosmic noon. During this epoch, galaxies had abundant cold gas supplies and experienced frequent interactions, leading to high star formation rates across the cosmos. Since then, galaxies have gradually used up or stabilized their gas reservoirs, leading to a decline in global star formation rates. Understanding how galaxies transition through these phases involves unraveling the complex feedback processes and environmental influences shaping star formation across time. On the scale of individual molecular clouds, formation and destruction cycles are tightly connected to the galactic environment. Spiral arms and galactic bars help gather diffuse gas into denser complexes, encouraging molecular cloud formation. Conversely, energetic feedback, galactic shear forces, and large-scale turbulence contribute to cloud dispersal. This continual cycling affects the observable star formation rate and patterns within galaxies. Recent large-scale surveys, like those conducted by the ALMA Observatory and the Herschel Space Observatory, are mapping molecular clouds both in our galaxy and in nearby galaxies, helping to quantify how such environmental factors control star formation efficiency. Furthermore, the role of cosmic rays, high-energy particles traveling near the speed of light, adds another layer to this interplay. These particles can penetrate molecular clouds deeply, influencing the ionization state and chemistry of the gas. Cosmic ray ionization can both heat the interiors of clouds slightly and catalyze chemical reactions important for molecule formation. The exact influence of cosmic rays varies between galaxies and within different cloud environments, but it is increasingly recognized as a significant factor in regulating star formation conditions. Another large-scale influence comes from the gravitational potential of the galaxy, particularly near galactic centers. Dense, dynamic environments around supermassive black holes harbor extreme conditions where star formation can be either enhanced or suppressed. For example, the Milky Way's center contains dense molecular gas clouds subjected to intense tidal forces and radiation fields. Despite harsh conditions, stars continue to form there, sometimes in unique ways. Comparable nuclear star clusters in other galaxies similarly display ongoing star formation activity, influenced by their extreme galactic environment. In addition to gas dynamics, magnetic fields on galactic scales extend well beyond individual molecular clouds. These fields shape how gas flows and condenses, influencing star formation patterns throughout galaxies. Measurements of polarized radio emission reveal magnetic field structures aligned with spiral arms or ordered large-scale geometries, suggesting a dynamic interplay between magnetism, turbulence, and gravity. These fields can help channel gas motions, influence cloud collapse, and modulate the feedback processes that regulate star formation on multiple scales. The study of star formation thus spans an enormous range of scales, from tiny dust grains within protoplanetary disks to entire galaxies bursting with stellar clusters. Integrating this wide perspective enables astronomers to understand how fundamental physical laws govern the transformation of diffuse cosmic gas into the luminous stars that shine across the night sky. Recent progress has been fueled not only by observational advances, but by sophisticated computer models simulating galaxies and star formation in unprecedented detail. These simulations incorporate physics ranging from gravity and hydrodynamics to magnetism, radiation transport, and chemical evolution. By modeling both large-scale galactic dynamics and small-scale cloud collapse simultaneously, they provide new insights into how star formation emerges naturally within the evolving cosmic web. As these theoretical and observational tools continue to develop, researchers aim to resolve long-standing questions. What precisely determines the efficiency of star formation under varying galactic conditions? How do feedback processes self-regulate the birth of stars to prevent runaway collapse of gas? What role does environment play in shaping the diversity of star clusters and planetary systems? Addressing these will deepen our understanding not only of star formation as a fundamental process, but also of galaxy formation and evolution across cosmic time. In essence, stars do not form in isolation, but as parts of a vast cosmic machinery where the life cycle of interstellar gas connects the scales of dust grains, planets, stellar clusters, and galaxies. Each new star born represents a node in this complex web, linking the microphysical processes of gas collapse and chemistry with the grand evolutionary story of the universe itself. By continuing to observe, model, and analyze these interconnected scales, scientists unravel the mechanisms by which the universe continuously renews itself, turning the raw material of space into the radiant stellar beacons that illuminate the heavens. A fundamental aspect emerging from the large-scale connections between star formation and the galactic environment is the concept of star formation efficiency, or SFE. This term refers to the fraction of gas within a molecular cloud that ultimately transforms into stars before the remaining material is either dispersed or consumed. Understanding SFE is critical because it controls how quickly galaxies convert their raw gas into luminous stars and shapes the galaxy's future evolution. Observations show that the SFE can vary widely. Some molecular clouds are extremely productive, converting a significant portion of their mass into stars over relatively short timescales. Others appear relatively inert, with low rates of star formation despite similar amounts of gas. Part of this variability arises from differences in cloud properties like mass, density, turbulence, magnetic fields, and environmental factors such as proximity to massive stars or the dynamics of the host galaxy. One key insight is that star formation is an inefficient process on average. Across the Milky Way, typically only a few percent of the total molecular gas in any given region ends up in stars before feedback mechanisms like stellar winds, radiation, or supernova explosions disperse the remaining gas. This inefficiency is a natural consequence of the delicate balance between gravitational collapse and opposing forces, as well as the active role of feedback in halting star formation once enough stars have formed. The interplay between efficiency and feedback forms a self-regulating cycle within galaxies. When star formation rates rise too quickly, the increased energy input from massive stars injects turbulence or removes gas from molecular clouds, effectively slowing or stopping further collapse. Over time, this feedback allows gas reservoirs to replenish and cool down, permitting star formation to resume later. This way, galaxies maintain a relatively steady cadence of stellar birth rather than exhausting their fuel in short bursts. Measurements of star formation efficiency across different galaxies provide vital data for understanding this balance. For example, in starburst galaxies undergoing intense episodes of star formation, the SFE can be significantly higher than in more quiescent galaxies. These bursts often result from galactic mergers or interactions that compress gas to very high densities, overwhelming feedback processes temporarily and allowing rapid star formation that can briefly outpace the usual regulatory mechanisms. On the other end of the spectrum, regions with strong shear forces from galactic rotation or harsh radiation backgrounds may have suppressed SFEs, as these environmental pressures inhibit cloud collapse or accelerate gas dispersal. This diversity highlights how galactic environments sculpt star formation activity on scales ranging from individual clouds to entire galaxies. Aside from efficiency, another critical parameter influencing star formation is the molecular cloud lifetime. How long a cloud persists, continually spawning stars before dissipating, directly affects the cumulative star formation in that region. Early theories proposed long-lived clouds, surviving tens of millions of years, but more recent observations favor shorter lifetimes, on the order of a few million years. This shorter timescale aligns better with the observed rates of star formation and rapid cloud dispersal, initiated by strong stellar feedback. Cloud lifetime correlates closely with cloud mass and environment. Massive giant molecular clouds in dense galactic regions may form stars vigorously before feedback disrupts them, while smaller clouds in quieter areas may exist longer but form fewer stars overall. Understanding the life cycle from cloud formation, star birth, feedback, to cloud dispersal is crucial for modeling how galaxies sustain star formation chronically over time. A related key factor is the formation mechanism of molecular clouds themselves. These clouds form from the diffuse atomic gas permeating the galaxy, but the transition from diffuse gas to cold, molecular structures capable of star formation involves complex physics. Gas cooling processes, turbulence, magnetic fields, and shocks from spiral arm density waves or supernova remnants all contribute to compressing and cooling gas, until molecules like molecular hydrogen, H2, and carbon monoxide form. Cold molecular gas requires effective shielding from ultraviolet radiation to survive and accumulate. Dust grains within the interstellar medium play a vital role here. By absorbing and scattering UV photons, dust allows molecules to form and persist. Consequently, dust also facilitates the cooling of gas by enabling emission of infrared radiation, further promoting cloud collapse. One interesting consequence of the molecular cloud formation process is that clouds often inherit properties from their galactic environments, such as rotation, large-scale magnetic field orientations, and turbulent velocity patterns. These inherited characteristics can influence the internal structure of clouds and ultimately the efficiency and mode of star formation within them. Zooming in further, research has revealed that molecular cloud substructure, particularly the dense clumps and filaments within clouds, is a major determinant of star formation activity. These substructures vary in density and stability, with the densest clumps often serving as the immediate precursors to star-forming cores. High-resolution observations across multiple star-forming regions confirm that the fraction of gas concentrated into such dense clumps correlates strongly with the star formation rate. In particular, studies using tracers sensitive to dense gas, like hydrogen cyanide, HCN, show a tighter relationship between dense gas mass and star formation than with total molecular gas mass. This finding implies that the amount of gas reaching high densities is the key regulator of how many stars a cloud ultimately forms, supporting models where local conditions within clouds, rather than cloud-wide properties alone, control star formation outcomes. Another important dimension to molecular cloud studies involves assessing the role of cloud collisions and interactions. Colliding clouds or cloud fragments may trigger star formation by rapidly compressing gas beyond critical densities, overcoming internal turbulence and magnetic support. Observational evidence suggests that such interactions could be responsible for some of the most intense star-forming regions in the galaxy. Indeed, giant molecular cloud complexes sometimes seem to form chains or associations where cloud-cloud interactions are common. Triggered star formation from such collisions may explain clustered or sequential star birth observed in some regions, adding new complexity to the classical picture, where gravity and turbulence dominate purely internally. Moving beyond individual galaxies, the environment on intergalactic and cosmological scales also influences star formation by setting the conditions for gas supply. Galaxies acquire fresh gas from the cosmic web, the large-scale network of filaments composed primarily of dark matter and diffuse gas. This inflow resupplies galactic reservoirs, enabling ongoing cloud and star formation. Conversely, processes such as ram pressure stripping in dense galaxy clusters or energetic outflows from active galactic nuclei can remove or heat gas, suppressing star formation by reducing the availability of cold material. Such environmental effects explain, in part, why star formation rates vary not just between galaxies, but within galaxies depending on their location in groups or clusters. The many scales and factors involved in star formation, from atomic gas inflows on cosmic scales through galactic dynamics to molecular cloud properties and internal physics, underscore its complexity. Yet they also highlight the interdependence of processes shaping the cosmos. Each star that lights the night sky is a product of this intricate cascade, linking the universe's largest structures with its smallest. As our observational tools improve, astronomers continue to uncover previously hidden facets of this grand process. Upcoming surveys spanning multiple wavelengths and employing cutting-edge techniques will refine measurements of molecular cloud properties, star formation rates, and feedback effects across diverse galactic environments, combined with sophisticated simulations capturing the interplay of physics from galactic to subparsec scales. These endeavors promise to clarify how stars emerge amidst the vast cosmic machinery. This rich understanding has implications beyond astrophysics. By comprehending star formation's regulation, efficiency, and environmental dependencies, we gain insight into galaxy formation histories, the prevalence of planetary systems, and the conditions that might foster life elsewhere in the universe. The dynamic cycle by which gas coalesces into stars, stars influence their surroundings, and galaxies evolve in turn, reflects nature's remarkable capacity to build order from chaos over cosmic time. In closing, star formation is not merely an isolated process occurring deep within cold clouds, but a cornerstone phenomenon woven throughout the fabric of the universe. Its study binds together the themes of structure formation, chemical enrichment, planetary origins, and the ongoing evolution of galaxies. Each step forward brings us closer to answering fundamental questions about our cosmic origins and the forces shaping the starry heavens above. Delving even deeper into how star formation shapes the cosmos, it's essential to recognize the role of metallicity. Essentially, the abundance of elements heavier than hydrogen and helium in influencing the process. Stars synthesize these heavier elements over their lifetimes and disperse them into space through winds and supernova explosions. Successive generations of stars, therefore, form from gas increasingly enriched in these metals. This enrichment affects many aspects of star formation, from the ability of gas to cool efficiently to the chemistry that governs cloud collapse and disk evolution. Metal atoms and molecules provide critical cooling channels within molecular clouds. When gas molecules collide, metals can radiate energy away more effectively than pure hydrogen or helium, allowing gas to reach lower temperatures and collapse more readily into dense cores. In the early universe, where metallicity was extremely low, molecular clouds were hotter and more diffuse, making star formation less efficient or favoring the formation of more massive stars. Observations of metal-poor galaxies and globular clusters offer glimpses into these primordial conditions, helping astronomers understand how the very first stars may have differed from those born in metal-rich environments like the Milky Way today. In addition to cooling, metallicity influences dust formation, the tiny solid grains made from metals and silicates that play a crucial role in shielding molecular clouds from ultraviolet radiation and providing surfaces for chemical reactions. Dust facilitates the formation of molecular hydrogen, the primary component of star-forming gas, by allowing individual hydrogen atoms to stick together on grain surfaces. Consequently, regions with low metallicity tend to have less dust, which hampers molecule formation and cloud cooling, thereby impacting the initial conditions for star birth. Moreover, metallicity affects protoplanetary disk properties and potential planet formation outcomes. Disks around stars with higher metal content tend to have greater amounts of solid material, increasing the likelihood of planet formation, particularly for terrestrial or rocky planets. This correlation has been substantiated by exoplanet surveys, showing that stars with higher metallicity more frequently host planets, especially gas giants. Understanding metallicity's role aids in assessing which environments might be more favorable for building planetary systems like our own. Turning to yet another dimension, the formation of massive stars introduces unique challenges and influences on their environments. Unlike their lower mass siblings, massive stars, those with masses 8 times that of the Sun or greater, reach ignition temperatures rapidly and exert powerful radiation pressure that can potentially halt accretion of material onto themselves. Despite this, massive stars do form, sometimes embedded deeply within dense clusters. One of the main puzzles for researchers involves how these stars overcome their own intense radiation to continue gathering mass. Theories suggest that strong accretion flows channeled through dense circumstellar disks can funnel gas toward the star in a way that mitigates radiation pressure, or that stellar mergers and competitive accretion within dense clusters contribute to building up mass. Observations of massive protostellar objects using radio and infrared telescopes continue to refine these models by revealing the structures and dynamics close to these young giants. Massive stars have profound feedback effects on their natal clouds. Their intense ultraviolet radiation ionizes surrounding gas, carving out large HII regions that glow in visible light and expand into the cloud. These regions can compress surrounding gas, potentially triggering a new wave of star formation in adjacent molecular material. Simultaneously, strong stellar winds and eventual supernova explosions inject mechanical energy into the interstellar medium, dispersing remaining gas and halting further star formation locally. This complex interplay means that massive stars both nurture and limit subsequent star formation, acting as regulators within galaxies. Beyond the immediate molecular cloud environment, the energetic feedback from massive stars can drive galactic-scale winds, contributing to the cycling of gas between galaxies and the intergalactic medium. Such outflows influence the chemical evolution of galaxies and their ability to sustain star formation over cosmic timescales. Understanding these larger-scale effects connects the life cycles of individual stars to the evolution of galaxies themselves. Studying these processes demands a full grasp of the timescales involved. While the formation of low-mass stars can take several million years, massive stars evolve much more quickly, reaching the main sequence in hundreds of thousands of years and ending their lives as supernovae within tens of millions of years. This rapid evolution shapes the structure and future prospects of their stellar nurseries in dramatic ways, emphasizing the importance of timing in the orchestration of star formation. Another emerging avenue of research concerns the interplay between star formation and dark matter halos, the invisible scaffolding that shapes galaxies. While dark matter does not directly participate in star formation, its gravitational influence governs how gas accretes into galaxies and their internal structures. The depth of a galaxy's gravitational well affects gas retention, cooling, and compression, thereby indirectly influencing star formation rates and efficiencies. State-of-the-art cosmological simulations now incorporate baryonic physics alongside dark matter dynamics to model galaxy formation and the embedded star formation within them, bridging scales from sub-parsec clouds to millions of parsecs across cosmic structures. Looking forward, one particularly exciting frontier is the characterization of star formation at the very earliest epochs of the universe. The first stars, called population III stars, formed from pristine hydrogen and helium gas without heavier elements. These stars were likely massive, short-lived, and crucial for initiating the chemical enrichment of the cosmos. Detecting signatures of these primordial stars remains a major goal for astronomers, with efforts focusing on distant galaxies and faint cosmic background signals that carry the imprint of early star formation. The study of star formation in diverse environments, including low metallicity dwarf galaxies, starburst regions, galactic centers, and the outskirts of spiral arms, continues to reveal the remarkable adaptability and variety of star-forming processes. Each setting offers a slightly different laboratory to test physical theories and understand how universal or variable star formation might be. Combining these studies helps build a comprehensive picture of how stars have formed throughout cosmic history, informing models from the local neighborhood to the farthest reaches of the observable universe. In essence, star formation operates as a multi-scale, multifaceted process, intricately linked to the chemical, dynamical, and evolutionary aspects of the cosmos. It weaves through the life cycles of molecules, dust, magnetic fields, radiation, and gravity, producing not only the dazzling stars that punctuate the night sky, but also the planetary systems and conditions that enable life. As technology improves and theory advances, our capacity to witness and understand star formation with ever greater detail propels us towards uncovering the origins and evolution of the universe's luminous architects. Building upon our understanding of how star formation unfolds across diverse environments and timescales, it becomes clear that studying the outcomes of this process, specifically the properties and life cycles of the stars themselves, completes the narrative. The stars formed within molecular clouds do not all share the same characteristics. Instead, they populate a broad range of masses, compositions, rotational behaviors, and multiplicity states. These stellar properties, in turn, influence not just their own destinies, but also the broader galactic context, including planet formation and subsequent generations of star birth. One of the most fundamental distinctions among newborn stars is their mass, which largely determines their temperature, luminosity, lifetime, and ultimate fate. Low-mass stars, including objects like red dwarfs smaller than the Sun, burn their fuel slowly and can survive for tens to hundreds of billions of years, significantly longer than the current age of the universe. In contrast, massive stars, sometimes exceeding 50 times the mass of the Sun, blaze intensely but briefly, exhausting their nuclear fuel in just a few million years before ending in spectacular supernovae. The initial mass of a star is thus a pivotal factor in shaping its evolution. Astronomers observe that the mass distribution of stars born in clusters or entire galaxies tends to follow a predictable pattern called the initial mass function, IMF. This function typically means there are many more low-mass stars than high-mass ones, reflecting both the underlying physics of cloud collapse and fragmentation, as well as the feedback-regulated nature of star formation described earlier. Beyond mass, other stellar properties such as rotation rate and magnetic field strength also vary widely and impact subsequent stellar behavior. Young stars often rotate more rapidly than older stars due to conservation of angular momentum during collapse. Rapid rotation influences magnetic activity, driving phenomena like flares and star spots that can modulate brightness and affect circumstellar environments. Over time, magnetic winds carry away angular momentum, causing stars to slow down as they age, a process well measured in clusters of different ages. Multiplicity, or the occurrence of stars born in binary or multiple systems, is another crucial aspect, with surveys indicating that a significant fraction of stars, especially massive ones, form in pairs or larger associations. These stellar relationships influence mass accretion, disk dynamics, and later stellar evolution, introducing complexity to star and planet formation processes. For example, interactions within binary systems can truncate protoplanetary disks or alter orbital configurations of planets, potentially affecting the habitability and stability of planetary systems. Studying young stellar objects across their formative years reveals changes in emission across the electromagnetic spectrum, offering diagnostic insights. X-ray and ultraviolet emissions, often enhanced in active young stars, give clues about magnetic activity and accretion shocks. Variability in brightness across multiple wavelengths informs researchers about episodic accretion events, disk obscuration, and rotational modulation. Utilizing space telescopes like Chandra and GALEX, alongside ground-based optical and infrared observatories, astronomers compile comprehensive pictures of these gradual but dynamic transformations. Another dimension involves the chemical enrichment inherited at birth, which reflects the local interstellar medium's composition at the time of star formation. Detailed spectroscopic analyses reveal the abundance of elements heavier than helium, known as metals in astrophysics, within stellar atmospheres. These abundances trace the star's ancestry, with variations reflecting galactic chemical evolution and migration. Metallicity affects not only stellar opacity and energy transport, but also the types of planets likely to form, as higher metallicities generally bolster solid material availability in disks. Turning back to the cluster environment, the evolution of stars unfolds amidst intense interactions and feedback. Massive stars often reach their main sequence quickly and begin ionizing their surroundings, while lower mass stars gradually shed their accretion envelopes and disperse their circumstellar disks. Over time, this collective activity clears the natal cloud, eventually leaving behind relatively gas-free star clusters that gradually disperse under gravitational influences. The timescale for this gas clearing typically ranges from a few million to 10 million years. The dispersal of gas has significant implications for clustered planets still forming within circumstellar disks. Without the protective cocoon of the molecular cloud, disks become more vulnerable to photoevaporation from external ultraviolet radiation, particularly in dense clusters hosting massive stars. This environmental effect can reduce the disk lifetime and impact planet formation timescales, potentially affecting the prevalence and architecture of planetary systems in different stellar populations. Studying the long-term survival of stellar clusters and their planetary systems also relates to the galactic environment. Clusters can remain gravitationally bound for hundreds of millions of years as open clusters, or disperse quickly, contributing stars to the galactic field population. Dynamical interactions, both within clusters and with tidal forces from the galaxy, drive this evolution. These mechanisms help explain why many stars, including our Sun, do not retain close associations with their siblings, but instead populate the broader galactic disk. Another important aspect concerns how studying populations of stars at different ages informs the timescales of star formation and early stellar evolution. Observations across multiple star-forming regions reveal that most stars form within a few million years, with some continuing as late as 10 million years. By examining age distributions, disk fractions, accretion rates, and rotation velocities, astronomers can reconstruct the stages of stellar youth and the processes governing disk dispersal and planet formation. High-precision photometric and spectroscopic surveys have enhanced this field, enabling detailed stellar characterization in young open clusters and associations. Data from the Gaia mission have been especially transformative, providing accurate distances, motions, and intrinsic stellar properties that refine cluster membership and age estimates. These findings deepen understanding of how star formation proceeds both spatially and temporally within molecular clouds and across galactic environments. In addition to isolated and clustered star formation, particular interest lies in rare but influential phenomena such as massive star feedback via supernovae and gamma-ray bursts. The explosive deaths of massive stars inject energy and newly formed elements into the interstellar medium, influencing future star formation cycles on large scales. Supernova shock waves can compress nearby clouds, triggering star formation or clear gas, suppressing it, depending on the circumstances. These catastrophic events exemplify the interconnected nature of stellar life cycles and galactic ecology. On a larger scale, understanding how variations in star formation across galaxy types and cosmic epochs affect stellar populations constitutes a vital frontier. For example, analyzing star formation in dwarf galaxies or low-surface brightness galaxies, which often have distinct metallicities and dynamics, informs astronomers about the limits and diversity of stellar birth in differing environments. Likewise, studies of distant galaxies across cosmic time help chart how star formation rates and efficiencies evolve as the universe matures. Advances in instrumentation, particularly in multi-object spectroscopy and wide-field imaging, empower astronomers to conduct comprehensive surveys of stellar populations in star-forming regions, clusters, and entire galaxies. These efforts paint statistical portraits of mass functions, multiplicity rates, elemental abundances, and kinematics, crucial for calibrating theoretical models of star formation and stellar evolution. Cross-referencing these data with simulations that implement detailed physics allows refinement of our understanding of star formation on both individual and population scales. Finally, linking star formation to the emergence of planetary systems brings the story full circle. The properties of stars, from mass to rotation and magnetic activity, interact with their disks, and influence planet formation and habitability. Young stars' energetic outputs can affect disk chemistry, planetary atmospheres, and the retention of volatiles critical for life. Furthermore, the environment of star formation, whether sparse or densely clustered, can impose dramatic effects on planet survival and development. As research continues, integrating stellar properties, star formation environments, and planetary system outcomes drives a holistic comprehension of how stars give rise to the rich complexity observed in the galaxy. From the collapse of gas and dust within clouds to the shining stars and nascent worlds they become, uncovering these connections illuminates the remarkable processes crafting the universe's luminous constituents and the potential habitats they foster. Another important dimension to understanding star formation lies in the study of stellar feedback, not just how massive stars influence their surroundings through radiation and winds, but also the subtler effects of lower-mass stars and their collective impact on molecular clouds. While massive stars often receive the spotlight due to their dramatic energy outputs and eventual supernova explosions, a more complete picture emerges once we consider feedback across the entire stellar mass spectrum. For instance, even sun-like stars, during their formative years, emit strong stellar winds and energetic radiation that can affect their immediate environment. These young stars often undergo intense magnetic activity, resulting in flares and coronal mass ejections, pumping high-energy particles into the surrounding gas and dust. When multiplied across hundreds or thousands of stars within a cluster, these effects can contribute significant energy and momentum, shaping the evolution of the parental cloud. Moreover, outflows and jets from protostars, those narrow, high-velocity streams launched along magnetic field lines, serve as another form of feedback operating early in a star's life. These jets inject turbulence and kinetic energy into the molecular cloud, stirring and sometimes dispersing gas in the vicinity. While jets clear cavities that can aid in reducing accretion rates on the forming star, they may also compress nearby gas, creating pockets ripe for subsequent star formation. This complex, sometimes paradoxical role means feedback is not solely destructive. It can both inhibit and encourage new star birth, depending on timing and location. Another subtle yet critical feedback mechanism occurs through the radiation emitted by intermediate mass stars that are not massive enough to form large HII regions, but still produce enough ultraviolet light to affect the chemistry and heating of the surrounding gas. This radiation can create photodissociation regions around molecular clouds, where molecules are broken apart and gas heats up, potentially influencing how and where the cloud can collapse further. Studying these radiation environments helps astronomers understand the layered structure of star-forming regions and the transitions between molecular, atomic, and ionized gas phases. On the cumulative scale, the combined feedback of many stars gradually reshapes the molecular cloud over a few million years. This process often leads to the dispersal of the natal gas, marking the end of active star formation in that particular region. Once the cloud material is sufficiently cleared, the remaining stars and planetary systems evolve primarily on their own, free from the gas and dust that once surrounded them. The timing and efficiency of this dispersal influence how massive stellar clusters become and how many stars remain gravitationally bound. In recent years, advances in computational astrophysics have allowed scientists to simulate these feedback processes with increasing realism. Models now include magnetohydrodynamics, radiation transport, chemistry, and even cosmic ray effects, enabling detailed examinations of how feedback from a range of stars sculpts the birth environments dynamically. These simulations bridge scales from the complex gas dynamics around individual protostars to the sprawling molecular cloud, helping to explain observed structures such as cavities, filaments, and triggered star formation sites. Triggered star formation itself is a topic of growing interest. This process occurs when the impact of feedback compresses neighboring gas pockets beyond a critical threshold, causing new collapse and star birth. Observations of bubbles and shells around massive star clusters, and the young stars forming along their peripheries, provide strong evidence that feedback processes can seed subsequent stellar generations. This ongoing cycle links star formation epochs, illustrating how stellar populations build upon one another across millions of years. On larger galactic scales, feedback mechanisms also connect tightly to the regulation of star formation rates and the overall life cycle of gas. Galactic winds driven by collective feedback from numerous massive stars and supernovae can remove gas from star-forming regions or galaxies altogether, influencing the evolution of galaxies over billions of years. These outflows distribute metals and energy far beyond their points of origin, enriching and heating surrounding intergalactic space. Observational evidence for galactic-scale feedback comes from the detection of fast-moving gas expelled from starburst galaxies and active galactic nuclei. By measuring outflow velocities, temperatures, and compositions, astronomers assess how efficiently feedback processes remove fuel for star formation, thereby contributing to the quenching of star formation in some galaxies. Understanding this regulation is key to explaining observed trends, such as the correlation between galaxy mass, color, and star formation activity. Returning to the birth sites of stars, another frontier involves examining the role of magnetic fields not just during cloud collapse, but throughout the entire feedback cycle. Magnetic fields influence how feedback energy propagates, how gas flows are channeled, and whether certain structures can resist dispersal. Observations using polarized light at multiple wavelengths are making it possible to map field configurations in exceptional detail. These studies reveal that magnetic fields can confine expanding bubbles, guide outflows, and stabilize filaments against disruption, all factors that tightly couple magnetism to star formation regulation. Complementing these physical insights, chemical diagnostics help trace the impact of feedback on molecular cloud composition. Molecules sensitive to shock heating, ultraviolet irradiation, or cosmic ray ionization act as natural probes of feedback environments. For example, increased emission from molecules like HCO+, CN, or CO can indicate shock-processed gas or regions exposed to energetic radiation. Comparing molecular abundances inside and outside feedback-affected zones reveals how star formation alters and resets the chemistry of the interstellar medium. Moving beyond the physics of stellar feedback, the influence of environment on star formation efficiency and outcomes remains an area of active research. Some regions of galaxies, such as dense spiral arms or galaxy centers, support higher star formation efficiencies due to enhanced gas compression and interaction rates. Others, like quiescent outer disks or dwarf galaxies, show lower efficiencies, possibly linked to differences in gas density, turbulence, magnetic field strength, or metallicity. Environmental effects are also evident in external galaxies, where diverse morphologies and interaction histories create contrasting star formation modes. For instance, galaxy mergers often trigger starbursts by funneling gas into concentrated regions, rapidly forming stars at elevated efficiencies. In contrast, isolated ellipticals with little cold gas content have nearly ceased star formation. Astronomers use multi-wavelength surveys to quantify how environmental factors, including radiation fields, cosmic ray densities, ambient pressure, and large-scale dynamics, modulate star formation. Understanding these dependencies aids in constructing unified models that apply throughout the universe, accounting for the remarkable variety of star formation regimes observed. Another compelling direction in star formation studies probes the interplay between star formation and cosmic time. By observing galaxies at different distances, and thus at different epochs, astronomers trace how star formation rates and efficiencies evolved as the universe aged. Data show that star formation peaked during an epoch called cosmic noon, roughly 10 billion years ago, followed by a decline as gas reservoirs became depleted or heated. Exploring high-redshift galaxies reveals contrasting conditions, such as lower metallicities, higher gas fractions, and intensified turbulence, altering the nature of star formation compared to the present day. Studying these early star-forming galaxies provides key insights into how the first generations of stars influenced their environments, contributed to cosmic reionization, and set the stage for subsequent galaxy evolution. As observational capabilities continue improving, next-generation telescopes and instruments promise to extend these studies with unprecedented sensitivity and resolution. Facilities like the James Webb Space Telescope, the Extremely Large Telescope, and future radio arrays will probe star-forming clouds and disks in distant galaxies, revealing the universality and diversity of star formation processes across space and time. In summary, star formation is fundamentally interwoven with feedback processes operating across a range of scales and stellar masses. From the outflows of individual protostars to the explosive deaths of massive stars, and the collective energetic outputs shaping galactic gas cycles, feedback emerges as a central regulator guiding when, where, and how stars arise. This dynamic interplay ensures that star formation remains a self-regulating, evolving phenomenon, intimately tied to the broader cosmic environment. Continuing to unravel these complex interactions enhances our understanding not only of how stars like our Sun formed, but also of the factors that govern galaxy evolution and the cosmic history of matter. By studying star formation in action, astronomers uncover the pathways by which the universe constructs and sustains its luminous fabric, revealing the profound processes that connect gas, gravity, chemistry, and energy across the cosmos.